Uh, Thanks, Noah. So yeah, I'm actually one of Noah's postdocs currently at Lakehead University, and I work on like a range of different topics to do with ductile deformation. But today I'm going to specifically be talking about some of the work that I did during my PhD, and I continue today, looking at measuring or quantifying the strength of lower crustal rocks, specifically those that are made of more than one mineral, which we refer to as polymineralic. So why do we care about the ductile portion of the continental crust? Well, everyone here obviously knows that the Earth is made up of plates, and the deformation tends to be localized in discrete zones at these plate boundaries, which you can see here. And so these plate fault zones or plate boundaries are made up of a brittly deforming seismogenic upper crust, which you can see here, a transitional brittle ductile portion, and then a ductilely flowing lower crustal region that we refer to as a shear zone. And from as way back as kind of 1985, people were thinking that these ductile portions of the crust and how strong they are and how quickly they deform influences the magnitudes of differential stress in the upper brittle crust and also therefore the deformation styles. So being able to understand the seismogetic portion of the crust, which is obviously has lots of implications for us as humans living on the Earth's surface, we need to be able to fully understand the ductile crust and to incorporate these into seismogenic models. So while being able to measure the strength of the brittle crust is fairly easy, we can actually get direct measurements of the brittle crust. Measuring the ductile crust or measuring the strength of the ductile crust poses a few more problems because obviously it's 10 to 15 kilometers deep in the Earth. So there are two ways that we can get at the strength of the lower crust. And one of them is through experiments at known deformation conditions. So this is a set of experiments from Kolstad from 1995, quite a long time ago, but it's still a wonderful experimental study. And so they have a differential stress on the x-axis and depth on the y-axis, and these are referred to as strength profiles when we construct them. And you can see we've got the brittle portion of the crust, which is this linear relationship here. But by doing deforming a bunch of materials that are meant to be representative of the continental crust, so quartz, and representative of the mantle, so olivine, we get these strength depth profiles during throughout the ductile portion of the crust as well. So you can see that these are getting up to differential stresses that are quite high, 500 MPa, which is potentially quite unrealistic for the strength of the lower crust in nature. And this discrepancy can be for a number of reasons. Firstly, we're looking at a single mineral, so monomineralic samples. In the case of continental crust, we're looking at quartz, which is supposed to represent the bulk deformation of continental crust, which is made up of loads of different minerals, which all interact with each other. The second is the fact that we have to extrapolate these to completely different conditions in nature. So in experiments, we're looking at samples that are maybe a few millimeters big, and we're looking at strain rates that are relatively fast because we need to see them within our lifetime. Whereas in nature, things are obviously a lot bigger and a lot slower. So the other way that people measure strength is that they go and look at exhumed lower crustal rocks or shear zones in nature and get measurements from the rocks that are seen there. And this is a combination from Bear and Platt in 2014 that went and looked at all the different studies at that point of all the different fault zones that were there, so normal, strike slipped, and thrust. And they could kind of put together the brittle portion that you can see here measured in green, and then the ductile portion for various different geothermal gradients. So again, you've got shear stress on the x-axis and depth on the y, and we can see that we get much more realistic stresses from these samples because we're actually measuring what's out there in nature. But there are problems posed with this method as well, which I'll go into more detail. But the main one is that you're not actually sure which portion of the deformation history you're recording because we're obviously not controlling that when you're looking at natural samples. So how are all of these stress measurements currently taken? Well, what we do is we use microstructures in nature that have a known relationship with stress, and this is a method known as piezometry. And by far the most prolific piezometer is that of the grain size of a rock. So here you can see a combination of all the different grain size piezometers that currently exist, and you can see that they're on a range of different materials from olivine, orthopyroxene, quartz, so lots of feldspars and calcites. And plotted here, you can see the recrystallized grain size against the equivalent stress, and that each of these piezometers have an inverse relationship with stress. That is, as you increase the stress experienced by a rock, the grain size reduces. And you should point out that if you're going to go and use piezometry, grain size piezometers can only be applied to recrystallized grains. So they're the newly fresh, undeformed grains within a rock, and you can't really use them on rocks that have experienced a little bit of deformation and therefore have intercrystalline, that have slight rotations in intercrystalline rotations. So if we normalize the recrystallized grain size by the Burgess vector and the equivalent stress by the shear modulus, you can see that they roughly collapse down onto a somewhat single relationship, at least with a single gradient, which is what theory would predict from this. The original theory of grain size piezometers would predict. So these are clearly extremely well-constrained methods of measuring stress. However, there is a huge limitation to grain size piezometry, and that is that all of these experiments are calibrated using a monomineralic sample, so ones that's only made up of the minerals that they're using. So here, for example, calcite or quartz in the cross one. And that when you introduce a secondary phase into the system, what that does is it causes pinning of the grain boundaries, thus preventing them growing. And this can lead to a smaller grain size than you would otherwise have in the rock. And therefore, if you use this in nature in a polymineralic sample, you would probably overestimate the stress because you'd have a smaller grain size than what would normally equilibrate with that stress. Thankfully, there are other microstructures that also have a known relationship in stress, such as subgrains, which is what I'm going to be talking about today. So here we've got that original theory that I said from Twiss 1977, which said that all piezometers should roughly collapse down onto a singular relationship. So he's normalized stress here and then normalized the length scale, which can be either a grain size or a subgrain size. And we can see our recrystallized grain size piezometer here, but we can also see that you get the same relationship with stress. That is that the higher the stress, the smaller the subgrains of a rock. So what are subgrains? They're the intergranular features or intergranular low angle boundaries within a grain. You can see a schematic here where the black is a grain boundary and all the gray are subgrain boundaries. And being intergranular, they should in theory not be affected by the presence of secondary phases. And there are other things in the literature that make subgrain size piezometry quite desirable. The first is that they supposedly require very little strain to equilibrate with the stress. Whereas, piezometry, grain size piezometry is meant to take a little bit longer. I think it's something like 20% strain off the top of my head. That could be wrong. It's been a while. And also that they're meant to be immune to the effects of annealing. So subgrains are meant to be resistant to moving or migrating when you're heating a rock after deformation. So there are subgrain size piezometers that currently exist. This is a similar plot than what I was showing you for grain size piezometry, except this time I've already normalized the subgrain size by the Burgess vector and the stress by the shear modulus. And what you'll note is in the 10 subgrain size piezometers that exist, 7 of them are olivine. So in theory, all of these should collapse down definitely onto a single relationship, but there is massive variety in the subgrain size piezometers that currently exist. And in part, this is potentially due to how people have defined subgrains across different studies and how they've measured subgrains across different studies, because the measurement size is very sensitive to the technique that you use. So here we've got a definition of what constitutes a subgrain from the Curato book in 2012. And that they, as I said, that they're intergranular structures that are enclosed by low angle grain boundaries and can be modeled as arrays of dislocations. So if you think that you're defining a grain size or a grain boundary as something that has between 10 or 15 degrees misorientation, that means your subgrain boundary could have anything from 1 degree misorientation all the way up to 15 degrees misorientation. And this is a study by Trimby, where they're looking at the critical misorientation angle used to define a boundary or define a domain against the domain size. And they were looking at relic grains, ones that have not been recrystallized, and matrix grains that you'd assume have been recrystallized. And you can see that the critical misorientation angle that you use to define a subgrain boundary massively affects the subgrain size that you record. However, that difference is relatively small at low critical misorientation angles. So if you're looking at kind of 1 degree or 2 degrees, there isn't much variation between the relic and the matrix domains. So one potential reason these studies don't match is because they're all using different ways of defining subgrain boundaries. And And so we want to create a new calibration where we're being very specific about the angle that we're using to define a subgrain boundary. And we also want to make it really easy to apply to lots of different rocks. So whereas with recrystallized grain size piezometry, you can only look at the matrix domains, we want one that you can apply to the whole rock. And therefore we will want the one that you can include these relic grains and these matrix domains. So we want to define a new subgrain size piezometer, which is 1 or 2 degree misorientation, or includes all subgrains that have 1 or 2 degrees of misorientation. And so I told you that the measurement method affects the subgrain size, or the method that you use to measure the subgrain size affects its size. So if you're using TEM or if you're using optical microscopy, by far the most prolific way of measuring grain size and subgrain size now is to use electron back scatter diffraction. So you can see this schematic here. This is set up within a scanning electron microscope, and you fire electrons at a sample that is tilted. They go into the crystal lattice and they're diffracted, and they're picked up on this phosphor screen, and you get diffraction patterns. And you can see this really nice schematic or a little GIF from Oxford Instrument, where it's going between different grains, and you can see that there are different diffraction patterns. And based on those diffraction bands, you're able to tell what phase it is and also the orientation. So you're able to get a really good constraint on all the different orientations within grains and within a rock. And here you can see an EBSD map showing those variation orientations in one of our samples. And the orientations are colored through this IPF figure. And the black boundaries show grain boundaries, and these gray boundaries, so subgrain boundaries. So there's not currently or wasn't currently a subgrain size piezometer calibrated for EBSD. So not only did we want to be really clear about what misorientation angle we were using to define a subgrain, we also wanted to use it in the modern technique of measuring orientations within a rock and use EBSD. So we took samples from actually 2 different minerals, and this was going on the theory from Twiss in 1977 that you should be able to get a singular relationship for multiple different minerals if you are able to normalize it by the Burgess vector and the shear modulus. And I showed you about kind of 15-20 studies of grain size piezometers. So from that, you can see that normally you have to calibrate a new relationship for every single mineral that you want to use piezometry on. But we thought if we tried to establish one that used multiple minerals, we could create a generality to any mineral that you know the elastic parameters for. So in this case, we chose olivine and quartz because they're the most abundant minerals in the continental crust and oceanic crust, respectively. And you can see here these local misorientation maps in olivine in red and in quartz in blue. Again, the black boundaries show grain boundaries, and all of these concentrations of color are showing you subgrain boundaries with misorientations up of anything over 3 degrees. So we did these, or I got these deformation experiments from actually other people. So there are published studies, one of which was the original calibration of the grain size piezometer in quartz. And they're over a range of different temperatures and a range of different stresses. And we measured subgrain size piezometry using a method called the line intercept method that you can see schematically up here. And this is where you draw a load of lines over your sample and you define a critical misorientation angle, in this case 1 or 2 degrees. And every time your line intersects with that critical misorientation, it put a point, and then it measures the mean intercept length between these points. And this is advantageous for subgrain boundaries because you're able to catch these really primitive early boundaries, which might not be closing to form a complete subgrain. But what you need to kind of get your head around is that it's the average spacing of any boundary that is greater than 1 or 2 degrees. So this also includes grain boundaries within the calibration. So here are the 2 results that we have. Again, we've got shear modulus normalized, the mean line intercept normalized by the Burgess vector and the shear modulus normalized, start again, 3rd time's a charm. We have the mean line intercept normalized by the Burgess vector and the stress normalized by the shear modulus. You can see in green, or in these squares and triangles, you've got olivine data, and in the diamonds and circles or pink, you've got the quartz data. And in log space, we get this really nice linear relationship for the 1 degree and the 2 degree. So we've calibrated this new piezometer through EBSD, and we've also shown that we can apply it to 2 minerals. Another advantage of this over grain size piezometry is that grain size piezometers and all of these piezometers, or all the grain size piezometers, are calibrated using what are referred to as pure shear experiments, where you're just pushing down from the top. whereas in nature, samples look a little bit more like simple shear experiments where we're going kind of top to the right. And in grain size piezometry, this is the simple shear versus pure shear geometry has shown to have a major effect on the grain size you get, and thus the grain size piezometers that you can use. Whereas in our experiments, if we break them up into axial experiments like pure shear and simple shear experiments, they actually still sit perfectly on that line. And therefore, this is also more applicable to nature because you don't have this geometric effect that you do have in grain size piezometers. So we calibrated these two new piezometers, one for 2 degrees if you have kind of a lot of noise in your data, and one for 1 degrees if you don't have much noise in your data. But there remains a number of questions that we wanted to test before we can kind of confidently use these in nature. And the first question, or the most prominent question, is, are subgrains truly immune to the effect of secondary minerals? So in theory, they're intergranular and they shouldn't be affected by secondary phases, but we want to be really confident about this. We want to test this and make sure that our piezometers are accurately measuring the stress within an individual phase. The second, which I was sort of talking about earlier when I was showing the stress strength profile by Platt and Baer, is the fact that we don't have steady state deformation histories in nature like we do in experiments when we calibrate these piezometers. And so we want to know, how do the rapid changes in stress modify the subgrain size? Are they able to kind of keep up with the stress to record it or do you tend to record different parts of the deformation history in natural rocks? And then the third one is, obviously, if we're looking at polymineralic rock, we're measuring the stress within an individual phase in that system. So we want to really know what the bulk stress of those rocks are. And so we need to know how the stress within an individual phase relates to the bulk stress experienced by the sample. So to address the first question, there is only really one sort of experimental setup that you can use, which uses an apparatus known as a deformation dia, where dia stands for diamond. And these are high pressure, high temperature deformation apparatus that are used to kind of probe the strength of deep earth, so mantle kind of conditions, and therefore use really, really tiny samples. So here you can see a schematic of the experimental apparatus and a cut through of what you see in the sample assembly, which you can see in more detail here. We have our pressure medium, we get temperature through a resisted graphite furnace, and then we have our pistons and our 2 samples in series here. And why we have 2 samples is because we want to have a control experiment, which is monomineralic, along with our mixed experiment, which is made up of 2 minerals, in this case, olivine and orthopyroxene, one that's used in the original calibration and one that hasn't been used in the calibration of the piezometer. So that control experiment is really important because if you look at the conditions of the experiments that we're doing, okay, they're roughly at the same temperatures as those used in our calibration, but they're at way higher mean stresses and way higher differential stresses. So we need to know that our piezometer can be applied to stresses way out of its calibration range before we can then test whether stresses whether it's accurately picking up stresses in individual phases in a polymineralic rock. So here's a few photos. I think this one was on the advertisement for my talk today, or some sort of variety of it is. These experiments, as I said, are very, very small. They're about 1 millimeter across because we're trying to get to, well, traditionally this apparatus is designed to get to really high pressures. So you can see me trying to construct one under a microscope, and then you can kind of see it sitted there before we put the anvils in. And so why we use this high temperature, high pressure apparatus is actually its situation on a synchrotron, so an X-ray source. And so by this way, we can fire X-rays at our sample and we can define a Bragg's angle and diffract them and pick up what we call diffraction spectra at 10 detectors downstream. You can kind of see the detectors down there. And this means that we're able to get in situ stress and strain measurements of our experiment. And so the way that we get stress measurements is that we get these diffraction spectra, which you can see here. And this is our monomineralic olivine sample. And so you've got intensity over the lattice spacing or the diffraction spectra. And you can see one of the spectras from detector 1 here and one of the spectras from detector 5. So they're at roughly 90 degrees from each other. And these represent the crystallographic planes within a mineral, and they're very unique to the mineral. They're kind of like a fingerprint of each sample. And you can kind of look at their spacing to get an idea of the crystallographic spacing, either, well, in the case of these 2 detectors, the vertical crystallographic spacing and then the horizontal D-spacing. And so by taking a kind of image of these at no pressure and no temperature, we can get what we call an open press diffraction. And then basing on the assumption that as you pressurize a rock, you compress it, and we know the kind of elastic strength of these rocks through, and we can work out, therefore, if we treat them all as springs, we can look at how much they constrict, and then we can look at the shift in the despacing, and from this we're able to get an idea of the pressure that these samples have been at. More interestingly, for what we're looking at is that if you then proceed to deform this sample in one direction, as you would in deformation, you would only get a shift in the vertical lattice spacings, and we can look at the offset between these two detectors, or look at the kind of difference in spacings between the vertical and the horizontal lattice spacing to get an idea of the differential stress. So that's kind of in the weeds a little bit, but what I wanted to highlight is here we're looking at just an olivine sample, but we can also look at mixtures, and we can see those olivine peaks here. So again, this is an intensity versus the despacing. And those 3 peaks, it's a little bit messy, but you've got these 3 peaks that were on the other slide, which are for olivine. But you can also see in this sample, we've got these orange peaks, which refer to orthopyroxene. So by looking at the stress on individual crystallographic planes, we're able to get the stress within individual phases in a polymineralic rock. And we also get what we call X-ray shadow graphs from this work. You can see an example of it here. And we put nickel foils, nickel being very heavy and therefore coming out very dark in X-rays, in between the pistons and the mixtures. And by doing cross-correlation between the the position of these nickel foils on shadow graphs throughout the experiment, we're able to get really high precision strain measurements as well. So to designing these experiments to address the question that we wanted to know, which is about whether our piezometer works at high pressure and also whether it works in polymineralic rocks, you can see that we did some steady state experiments similar to those that you use in the initial calibration. So these are where we're just doing one temperature, one deformation speed to kind of keep stress as constant as possible. So you can see here the differential stress against the strain. Here for the olivine stress sensor, I show that there were 3 peaks, and so we actually get stresses from each of those 3 peaks, which are plotted here. And then you've also got the Hasfigite, and in this case, you've got stresses from the 3 orthopyroxene peaks as well. But one of the other questions that we wanted to address was, how does subgrain size respond when you have non-steady state conditions? Are they able to kind of keep up the stresses? So we also included experiments in our analysis that had complex stress histories. And this was either through a temperature step or a change in the rate of the experiment. So you can see one here with the temperature step where you're starting at a nice steady state stress at this kind of 1,100 degrees. We increase the temperature and we see the relaxation of the stress to a much lower one. We also, because we're looking at kind of stress partitioning, we used obviously the 100% olivine samples as our control, but we actually used a range of different proportions of olivine and orthopyroxene, all the way up into one that was nearly completely orthopyroxene. And as you can see, this resulted in a range of different grain sizes throughout our rocks as well. So these are phase maps, obviously olivine in green and orthopyroxene in orange. And so here is a local misorientation map from one of our samples. And again, you've got orthopyroxene in orange and olivine in green. Probably don't need to keep repeating that. And you can see with these white boundaries, which represent our 2-degree subgrain boundaries, that you've got loads of substructure within the olivine. However, there isn't really any substructure within the orthopyroxene. So we haven't actually got any subgrains to compare to, sadly, really, in this mineral. However, taking another example, which is this, in this case, it's just the load cell, so it's completely olivine, you'll see that subgrains are very sparse in this sample and they don't actually exist. Or they don't meaningfully exist. And so potentially in this case, you're at a lot higher temperature, so your stress is going to be a lot lower. And these experiments are on really, really small samples, so our grain size is really tiny. And so this gave us the idea that potentially in some of these experiments where your stresses are very, very low, the predicted subgrain size from the piezometer is probably greater than your measured grain size in the rock. So we don't want to include samples which theoretically shouldn't have subgrains in, because we're only really interested in testing when subgrains exist. But we wanted to find an objective way of removing certain data from our study. And so we did this by basically predicting the subgrain size from the last increments of stress in the study and comparing it to the measured grain size that we had in the rock. And so if the stress was so low at the end of an experiment that the predicted subgrain size from our piezometer would have given a subgrain with a diameter way bigger than our grain size, we were like, okay, you cannot form subgrains in those rocks, and so we removed them from our data set. And we're going to start by just looking at olivine, and we're going to start by looking at the final stress experienced by the rock, because in theory, all the literature says that subgrains should be able to measure, very quickly respond to changes in stress, and so should be measuring the last increments of stress in a deformation history. And so that's this kind of slightly complicated figure here, which I'm going to talk you through, so hopefully it becomes clear. In this case, your ex situ stress is the stress measured through subgrain-size piezometry. And your in situ stress is the stress measured through X-ray diffraction, and that's on the last increments of deformation that's experienced by the sample. We have three examples here because, as I said, there are 3 different diffraction peaks that we're measuring stresses in, and we wanted to compare the subgrains to all of them. And then this black line represents the one-to-one relationship between the ex situ stress and the in situ stress. We have in green our stress sensor examples. So these are our control experiments, which in theory should fall on the line, and in the one I'm indicating very nicely falls on the line. And then we have our Hasbergite experiments where you've got olivine within a mixture, so olivine within a Hasbergite. And those are outlined in orange. And we can see, especially with this 130 peak, that they actually fit very beautifully on this one-to-one line. There's a slight offset up here with this experiment, but I've also sized the experiments based on the amount of strain, total strain that was experienced by it. You can see that this is actually one of our low strain samples, but kind of sits fairly off the line in 130, but does fit very near the line when you consider this 112 peak. The black open symbols that you can see are responding to those situations I said earlier, or represent those situations I said earlier, where you have a subgrain size or a theoretical subgrain size that is larger than the grain size of the rock. So in these cases, the stresses are extremely low and the grain sizes are also extremely small. So you kind of can ignore these open symbols that are presented. And why I want you to focus on this 130 peak is that we're getting different stresses from all of these different crystallographic planes, and that is because olivine is a non-isotropic sample or a non-isotropic mineral. And there have been a study that has been published, it's actually not a study I have done, which has looked at comparing the stress that is experienced by an isotropic mineral, so garnet, in which case the stress in every direction is the same, to the stresses that you get for different crystallographic planes in olivine. And they actually found that this 130 peak best represents what you would assume to be the bulk stress in olivine. So we're quite confident or comfortable or happy with the fact that we've got a really nice linear relationship in olivine, and therefore we can say that because we have this strong correlation, we are very confident that our subgrain-size piezometer is actually measuring the stress within individual phases within a polymineralic rock. However, some of the samples that I showed you earlier that in theory shouldn't have subgrains in them did have subgrains in them. So all of that work I was showing was the last increments of stress, showing that subgrains are able to kind of keep up with the changing stress conditions of an experiment. And here I'm giving you one of the samples that if you looked at the kind of grain size of the final rock and the final stress, the grain size was way too small to contain subgrains that were in equilibrium with the final stress experienced by a rock. But if you look at it, we can clearly see in the olivine that you have all of these subgrain structure. So this presents the question that in some instances, such as this, are we actually recording a different proportion of the deformation history within our subgrains in olivine? And this would link into other studies, where this is one from 1980 from a scientist called Ross, and she looked at basically measuring the differential stress and the subgrain size as you change conditions, and the arrows indicate the kind of deformation stress history. And she found that in paleoblasts, so not in recrystallized grains, you actually record the highest stress experienced by the rock. So they're unable to coarsen in paleoblasts, is what her prediction was on subgrain size. So we obviously found that subgrains are able to coarsen, but in these situations where we drop the stress to really low and we have really small grain sizes, are we potentially recording in a very specific set of conditions a different part of the deformation history? So these are the experiments that we didn't include. We kind of had excluded from our analysis because the grain sizes were too small. And again, we have the subgrain-size piezometer stress measured against the X-ray diffraction stress at various different peaks in olivine. And here, similar to how Ross did her figure in the previous slide, I plotted the peak stress, or the maximum stress experienced by a sample, and then the final stress experienced at the end of the sample. And you can see the stress histories with these arrows, with the black arrows representing a change in stress that was the result in a change in strain rate, and the red arrows indicating a change in stress that's associated with a temperature rise. And what's interesting is that in these stress histories where we drop the stress very quickly using a change in strain rate, you actually are recording the peak stress that is experienced by the sample. But when we're looking at a change in temperature, which is associated with a temperature rise, you can see that the subgrains kind of record somewhere intermittently between the peak and the final stress. So this shows that potentially when you increase, or you have stress drops that result from an increase in temperature, you can get some sort of coarsening, potentially annealing. But in these situations where you suddenly drop the stress in strain rate in very fine grain rocks, then potentially you can record these peak transient stresses that are experienced. And this would be relevant if you're thinking about very high stresses that are associated with earthquakes, that potentially you could be recording those in really fine grain regions of a shear zone. So what about orthopyroxene? Well, orthopyroxene was not used in the original calibration, but can we use our generalized relationship to sort of can we use it to see if our generalized relationship works for other minerals? I'm going to show these results. I would say that there are not many subgrains in orthopyroxene. So again, this is one of those figures. Hopefully they're becoming a bit more easy to read now, with subgrain size against X-ray diffraction size. In this case, I put both the peak stress and also the final stresses, and I've done open signals symbols for those which have a really low stress and a really small grain size, so that where you wouldn't necessarily expect there to be subgrains in them. And this is very, very messy and doesn't really show a relationship. So actually what I kind of want to conclude from this is that we can't yet tell whether our orthopyroxene is accurately captured by our calibration, partly because we haven't really got any subgrains within our samples. And that's demonstrated here. You can see these are all the different experiments, and other than a very few samples that are done at low pressure and temperature conditions, most of the orthopyroxene is very bare, which is potentially because it's not deforming at all. However, other work that has been done by Wiseman on NGO has shown that you can use our calibration on other minerals. So this was some experiments that he did where he normalized the subgrain size and normalized the stress and plotted our 1 degree piezometer, and then did a load of experiments on periclase, so MgO, and found that certainly within error, it sits really nicely on our generalized relationship. I unfortunately wasn't able to get the data together for this talk, but I've actually just come back from doing some experiments on halite at the University of Cambridge. And these also show that we can use our subgrain size piezometer to accurately measure the stress within halite at very low stresses. And that's kind of key because we have a very finite calibration range for our piezometer. But in these experiments that I've just presented you, we can show that it does apply to very high stresses way outside its calibration zone. And in these new results that we've got have actually shown that it also applies to very low stresses outside of its calibration zone, which is key for natural rocks, which tend to be deformed at much lower stresses than those that we see in experiments. The final thing I wanted to talk about is stress partitioning and how subgrain size piezometry correlates to the bulk stress that's experienced by a rock. And unfortunately, because we don't have any subgrains within our orthopyroxene, we can't in this study use subgrain size piezometry to look at stress partitioning, but we can use the X-ray diffraction data that we had. So here's the X-ray diffraction data in orthopyroxene against olivine. You get these large squares because we're looking at the maximum possible stress measured from one of the diffraction planes versus the minimum stress measured from a diffraction plane. And I realize that's sort of an ambiguous way of saying it. I mean that we have these 3 stresses from 3 different diffraction peaks, and we want to look at which we want to take the smallest and the highest and give it a range, and that gives us a range in orthopyroxene and olivine. And then we can kind of compare them. And for these high stress experiments where you would expect orthopyroxene to be stronger than olivine, you see that the orthopyroxene is experiencing or supporting a lot more stress than olivine. But as you get to the lower pressures, their strength seems to become more similar, and you actually get kind of a more even stress between the two of them. So if we want to see how subgrain-size piezometry can look at stress partitioning, we want orthopyroxene to be deforming. So we're going to target experiments done at lower pressures where we have a higher chance of deformation occurring in orthopyroxene, because from this, it looks like their strengths are relatively similar. And to do this, we use a different piece of apparatus known as a Paston apparatus. And these are a gas medium. Is a gas medium apparatus that goes to about 300 MPa. You can see me screwing in the top of one of them here. They have to be contained within these blast containers because they can essentially blow up. So slightly dangerous, but great fun. And here you can see a schematic of the sample assembly. And you'll notice that in these samples, they're a lot bigger than the D-dia ones, thankfully. You kind of 10 millimeters across and 25 millimeters long. And here you can see us cutting through one of our experiments after we've deformed it with that lovely green that we associate with San Carlos olivine. And so what I wanted to do here is I wanted to explore models of stress partitioning at constant strain rate. So this is a schematic from Li et al. In 2011, and it shows the average stress experienced by a sample versus the volume or volume fraction of particles. So in black, you can see their kind of matrix or their average bulk stress. And then in orange, you can see their particles, which we would equate to orthopyroxene, which is our strong mineral, and their composite, which is what we would equate to olivine. And so this is the idea of like, how do these stresses average out to give you that black or the bulk stress based on various different models? And we want to test the theoretical models that currently exist for this stress partitioning to maybe get a better idea of how we apply subgrain-size piezometry to natural rocks. So to do this, we need to have experiments that all deforming at the same strain rate and hopefully in the same deformation mechanism, which we'll get into in a second. So we think that orthopyroxene is going to be our strongest experiment. So we did that one first. And here you can see the differential stress versus the strain for all the experiments that we were able to do. Sadly, it was COVID, so it happened about a week after I started this project, hence that there are only 3. And so we started with our kind of 100% orthopyroxene, which in theory should be strong. And we did it at a constant stress to get a strain rate. And then we took that strain rate and did all the other experiments at this constant displacement rate that should roughly cause you to have a constant strain rate. And you can see we've got 3 different compositions, a 93% orthopyroxene, a 40% and a 20% orthopyroxene. And in the cases, the 2 end members where you've got either dominantly olivine or dominantly orthopyroxene, they're roughly the same differential stress. But when we have this mixture of the 2, you'll see that it massively drops to a lower stress at the intermediate compositions. So to truly compare this data, we need them to be at all the same. We need to normalize for a few parameters that affect strength. And this brings us on to these flow laws, which is how we describe the general behavior of different rocks under different deformation mechanisms. And so these are, you get the strain rate, and that's a function of the stress to a stress exponent, the grain size to a grain size exponent, the activation energy, and this material dependent constant, which is A, and then the temperature and the gas constant. So that's quite a lot of jargon, but basically what we're interested in is we want to make sure that we're comparing the relative stress of these experiments at what you would have as the same grain size, because grain size is going to vary between these when you have different compositions of olivine and orthopyroxene, and at exactly the strain rate, same strain rate, because you'll see that we actually have a slight variation in strain rates due to our how big the assembly was and how, etc., and kind of experiment by experiment disparities. So we don't know the deformation mechanisms that these are exactly occurring on. There aren't kind of very well constrained flow laws for polymineralic rocks. So we can basically normalize our stress using a variety of different deformation mechanism flow laws. So here is an example of one. This is not normalized. That's maybe the wrong word. So we work out the stress based on the flow laws for what you would expect in all of these different compositions if you had exactly the same grain size and exactly the same strain rate. And so here you've got that differential stress against the percentage of olivine and orthopyroxene. And we've done this for 3 different deformation mechanisms. One, which is dislocation grain boundary sliding with subgrains. And you can see the N and P parameters for that. Then you've got dislocation grain boundary sliding without subgrains, and then diffusion creep. And I've also plotted two end member models for how stress partitions or how stress partitions within polymineralic rocks. So I said we wanted to compare to these two end members. And this is basically the principle that if you have an aggregate with two different phases, do you have uniform strain rates at those boundaries? So each phase is experiencing the same strain rate, but different stress, or is stress uniformly distributed between those phases and you actually get different strain rates in the different minerals? So these two end members are also plotted. And you can see that whereas our kind of nearly 100% ortho-olivine and nearly 100% orthopyroxene sit quite close to these end members, especially in this diffusion creep field, our intermediate phase, which is a mixture of olivine and orthopyroxene, is very far off our models with massive weakening compared to the two end members. And if you plot these data, there's quite a lot in the kind of percentage of frame boundaries for the there's this differential stress against the percentage of phase boundaries. So the one that doesn't have, this is the 83% orthopyroxene, so it doesn't have many phase boundaries. There's quite a disparity in those stresses here, but we're probably not in diffusion creep, which is the orange one. So if you just look at these the circle and the square, what you'll see is that the overall strength of the sample drops off massively after you get to kind of a critical amount of phase boundaries, which has also been said in the literature to be about 40%. And so this weakening effect has actually only been seen in rocks that are kind of made with natural samples, so San Carlos olivine for olivine and Bramble orthopyroxene. And if you use a synthetic mixture of olivine and orthopyroxene, you don't actually see this weakening effect. So people have kind of suggested that this weakening happens to impurities within the rock that are segregated at phase boundaries and hence kind of enhancing phase boundary diffusivity. This, we're not presenting, or I'm not here to talk about mixing models and weakening effects, but what I wanted to present this data to you before is that you can see that in this case, models are breaking down. These end members of uniform strain rate and stress aren't kind of accurately measuring the stress within intermediate phases, and therefore it becomes even more important that we're able to measure the stress within individual phases and try and get an idea of the bulk strength of the rock through techniques such as subgrain-size piezometry. So looking at subgrain-size piezometry, here are the three samples when you look at the microstructures. And even though we were doing these at lower pressure to try and get subgrains within our orthopyroxene this time, we still don't see much structure within our orthopyroxene in the two mixtures that are mostly olivine, but we do see subgrain boundaries in our olivine, and we do see subgrain boundaries in our orthopyroxene. But what we can do is we can measure the stress using subgrain-size piezometry in the samples where we have subgrains and compare that to the bulk stress that we are seeing in the rock. And that's what I've done here. You've got differential stress on the y-axis and proportion of olivine and orthopyroxene on the x-axis. And the bulk stress is these black circles. And then you've got in the kind of green triangles, you've got olivine subgrain-size piezometry, and in the orange, you've got orthopyroxene. And what we can do, even though we can't measure stress from subgrain-size piezometry in two of the orthopyroxene samples, is that we can use kind of work out what we would expect the stress be if you needed it to average out at the bulk stress experienced by the sample. And interestingly, what we can see in this case is the stress from olivine is very stable, and therefore the orthopyroxene in the mixtures must be contributing to or causing all of the weakening in that rock. And if you think about what I said about kind of diffusion at phase boundaries being enhanced at intermediate compositions of olivine orthopyroxene, and the fact that we don't see any substructure in orthopyroxene, we can kind of hypothesize that potentially this orthopyroxene is deforming by diffusion creep, and that therefore you're getting all this weakening in the intermediate phases because of diffusion creep in orthopyroxene. This doesn't necessarily give you a hard and fast rule of how to apply subgrain-size piezometry to polymineralic rocks when you want to know the bulk stress, but does give you an example of how powerful subgrain-size piezometry can be in stress partitioning. And now, saying that I don't have a hard and fast rule to apply rocks subgrain-size piezometry to rocks that are made up of multiple minerals, I'm now going to go on and just use subgrain-size piezometry on rocks that are made up of multiple minerals. And this is I apologize because I know Canadians do a lot of field work, and this is like I'm coming to the end of my talk, and this is the only field work that I'm presenting. But this was actually my first interaction with Canada before I moved here in 2022, whereby I went and did some field work as part of my PhD on the Great Slave Lake Shear Zone in the Northwest Territories. And why we were particularly interested in the Great Slave Lake Shear Zone is that quite uniquely, it was an active shear zone whilst exhumation was happening. And therefore, as it exhumed and the rocks got colder and therefore they got stronger, you had localized deformation whilst preserving these older periods of deformation in the surrounding rocks. And that if you now look at the surface of what's exposed at the Great Slave Lake, you can see almost a depth profile through a transcurrent fault preserved beautifully at the surface for us to go and measure. So this is potentially going to provide, or it is giving us the ability to provide a strength depth profile through a strike slip fault that kind of are very rare in nature. And that's what you did. You can see the kind of large scale units here with upper amphibolite in red and the lower amphibolite in blue and some green schist. There's also some granulite facies, but we didn't use those in our transect. And here are the samples that we went across. So we walked across this sample and took a load of samples enabled to, that was a terrible sentence. We walked across this transect and took a load of samples to do subgrain-size piezometry on quartz, which we obviously used in our initial calibration. And so before we got the stress measurements, we obviously need to know a depth measurement. And for this, I invited Brendan Dick at the University of British, well, he was at Simon Fraser at the time, but who's now situated at the University of British Columbia, Okanagan, to be our metamorphic geologist on the trip. And he produced this great pressure temperature diagram, which shows that the kind of there is a single metamorphic gradient associated with the final deformation conditions of about 1,000 degrees per GPa. So if we can measure the temperature in our rocks, we can then get a depth using this geothermal gradient, and then we can correlate that to the strength of the rocks through subgrain-size piezometry. So we measured the temperatures in a number of different ways. The first is where we couldn't do PT measurements very specifically. We used the quartz microstructures that were present in the rock. So these don't give us an absolute temperature, but they give us a temperature range. And you can see here the three different examples where we've got subgrain rotation recrystallization, we've got a combination of grain boundary migration and subgrain rotation recrystallization, and then purely grain boundary migration. And using previous analysis, we can say, okay, because we have these types of recrystallization in quartz, we know roughly the temperature. But we were able to do temperature pressure estimates in specific samples. And we actually did a range of different temperatures with the idea that we'd get a much more accurate temperature estimate using lots of different methods. However, we didn't quite see that. So here we've got temperature plotted against all the different samples that we were able to do it in for the upper amphibolite and the epitote amphibolite. And the grey boxes represent the microstructures in quartz and the temperature ranges that we're getting for them. And what you'll see is that when you're looking at kind of TI in amphibold or amphibold plagioclase, we're actually getting temperatures that are way higher than what would be predicted from our microstructures and what we see in the quartz. And actually the only geothermometer that's kind of accurately measuring the temperature is this TI in quartz one by Thomas et al., which takes pressure into account, which is really important because at least from my experience of looking at studies that have used piezometry, they tend to kind of just pick a thermometer that works. So if they have amphibold and plagioclase, they use amphibold and plagioclase and say, okay, this is the temperature of deformation in the rock. But what we're clearly seeing here is that amphibold and plagioclase thermometers don't keep up with the temperature as you deform, and that we therefore need to think more carefully about which thermometers we're using when we're trying to predict the final increments of deformation or the depth of the final increments of deformation. So we're going to use TI in quartz thermometry, and then where we have it or where we were able to have it, because obviously you need a titanium-rich mineral to apply this, such as rutile, and then use these broad temperature ranges from the microstructures to get a depth where we don't have, unable to do TI in quartz. So here are some of our microstructures. I had just spent most of this talk telling you how difficult it is to apply subgrain-size piezometry to, well, not difficult, but how difficult it is to infer bulk stress from subgrain-size piezometry. So we were using regions which were mostly made up of quartz, which is quite similar to grain size and one of the criticism I used for grain-size piezometry. However, at least in this situation, we don't have to distinguish between relic and recrystallized grains. And hopefully it will open up once we are able to do piezometry on more minerals and get better models for how stress partitions. You would be able to do it even in a highly polymineralic region. But in this case, we're looking at regions that are mostly made up of quartz. And here you can see representative microstructures across a range of different facies, from green schist all the way up to granulite. And you can see that we have these beautiful subgrain structures within all of them. So putting it back onto way back at the beginning of this talk, where I was giving you that strength depth profile of all the different studies from 2014, which I do realize now is 10 years ago, so maybe I should go around updating that. We plotted our data on top of Platt and Bear's 2014 study, and you can see that here in the temperature profile. So we've got shear stress against temperature in this case. And most of the data fits relatively nicely on this curve, but you'll notice that actually our data seems to be shifted somewhat to the right on these higher strain rates of 10 to the minus 11 and 10 to the minus 12. And so this is indicating that our shear zone is potentially a higher stress, higher strain rate shear zone than those that you see in nature. And one explanation of this could be that, you know, there are not many full strength depth profiles of strike slip faults. So potentially strike slip faults are just stronger than normal faults and reverse faults. Or it could be that you are seeing different stresses recorded in grain size piezometry, which is what all the rest of the data uses to measure stress, and subgrain size piezometry. And this is particularly relevant if you look at this one study, experimental study by Silomone in 2020, where they used recrystallized grain size against stress. And in this case, they deformed the sample at steady state, or they did a load of experiments at steady state to test that they did fit on the piezometer. And then they did a load of samples at steady state, and then they kind of started reducing the temperature at specific temperature gradients, which caused an increase in stress. And what they found is in those situations, which they were trying to replicate exhumation of rocks, so temperature decreasing and strength increasing, is that the grain size piezometers were unable to keep up with the stress and actually gave a stress that was lower than the final stress experienced by the sample. So maybe our higher stresses are the result of the fact that we're measuring the last increments of stress, whereas grain size piezometry can't really keep up with exhumation and is therefore showing a lower stress representing of an earlier point in the deformation history. So this is work that I'm that is still ongoing. And so I've only done a very small amount of grain size piezometry to my samples, because as I said, I collected them thinking I'd do subgrain size piezometry, not grain size piezometry. So they're not all necessarily very well designed for grain size piezometry. But this is just showing our equivalent stress based on subgrain size and our equivalent stress based on grain size. And contrary to what we would expect, where I was kind of hoping that the grain size piezometer would show a lower stress, which would match what I just said in the previous slide, we actually find that the grain size piezometers are showing a higher stress for the case of the 2 degrees, or roughly the same stress if you're looking at 1 degree. So this links us back into, obviously I need to do more work, but maybe there's something about the Great Slave Lake where it's a particularly strong shear zone, or maybe it's maybe I need to do more grain size piezometry because it's only looking at 3 samples in this case. Very much ongoing work, but definitely something to think about if you're looking at complex systems and applying various different types of piezometers to them. So I think I'm 4 minutes, so very close to being over. But I hope, just to summarize, we calibrated a new subgrain size piezometer. We kind of proved that it works for polymineralic rocks. We've proved that it works both at higher stresses than used in the calibration, at lower stresses than used in the calibration for minerals that weren't used in the calibration. It's a really effective tool for kind of trying to quantify stress partitioning in polymineralic rocks. And I would urge, if this is a topic that I think I personally want to work on more, but sort of getting better flow laws or better stress partitioning models for looking at natural samples to try and get an idea of the bulk stress. A warning that traditional geothermometers may not actually be measuring the temperature of deformation. And potentially strike slip faults are stronger than their normal and reverse equivalents. I have just created my website, but it's very much in the early stage. But just to say, if you are interested in piezometry and you have any questions, please feel free to reach out to me. But also, I'm hoping to put, in the coming months, put some more resources on my webpage about applying piezometry correctly to rocks. And so there should be, at the moment, there is not an overview, there's only just an overview, whereas there's hopefully going to be a few pages that are dedicated to piezometry and how to use it in rocks, which hopefully would be a good resource for anyone who's trying to use it in their own studies. And that's me.